Hello students, this is Dilip Udhani. Today I will teach you three topics of vector calculus and one of them is arc length of a curve in space. When a curve is parameterized by taking values of t from some interval a to b, the position vector r bar t of any point t on the curve can be written as r bar t equals to x of t I cap plus y of t j cap plus z of t k cap. Then the tangent vector r bar dash t is given by r bar dash t equals to x dash t I cap plus y dash t j cap plus z dash t k cap. X dash t is derivative of x of t, y dash t is derivative of y of t, and z dash t is derivative of z of t. Now modulus of r bar dash t, that is equals to square root of x dash t square plus y dash t square plus z dash t square. Hence the arc length of parameterized curve is given by s equals to integration from a to b modulus of r bar dash t dt. If the curve is given to you in parametric form, then this is the formula to find out its arc length. How? I will make you understand with the help of example. Consider example number 1. That is, we have to find out the arc length of the portion of the circular helix r of t equals to cos ti plus sin tj plus t k cap from t equals to 0 to t equals to pi. Now this curve is in parametric form. So the arc length is given by s equals to integration from a to b modulus of r dash t dt, right? So here the value of a is 0 and b is pi. So it will be integration from 0 to pi. Now modulus of r bar dash t, that is square root of x dash t square plus y dash t square plus z dash t square. Here x of t is cos t, so its derivative is minus sin t. Y of t is sin t, so its derivative is cos t, and zt is t, so its derivative is 1. Now minus sin t square, that is sin square t, and this is cos square t plus 1, and sin square t plus cos square t is nothing but 1, and 1 plus 1 is 2. So square root of 2 is a constant value, and that will be as it is, and integration from 0 to pi dt. Now integration of 1 with respect to t, the result is t, and the upper limit is pi and the lower limit is 0, so it will become pi minus 0, and pi minus 0 is pi, and pi multiplied by root 2, the result is root 2 pi. So this is the required arc length, right? Now we will take y equals to function of x. Now if y equals to function of x is given to you, then arc length is defined by integration a to b square root of 1 plus dy by dx the whole square dx. Okay. So consider example number 2, that is we have to find out the length of the curve y equals to log sec x from x equals to 0 to x equals to pi by 3. Now this curve is of the form y equals to function of x, right? Now to find out the arc length for this curve from x equals to 0 to x equals to pi by 3, we will use this formula, right? That is integration from a to b square root of 1 plus dy by dx the whole square dx. Here the value of a is 0 and the value of b is pi by 3. So square root of 1 as it is plus dy by dx. dy by dx of y equals to log sec x. Now derivative of log x, answer is 1 upon x, and in place of x we have sec x, so it is 1 over sec x, and in place of x we have sec x, so again we have to differentiate sec x with respect to x, and derivative of sec x is sec x into tan x. So sec x will cancel out, the result is tan x the whole square. So it will become square root of 1 plus tan square x, and 1 plus tan square x is sec square x. So it will become integration from 0 to pi by 3 square root of sec square x dx, and square root of sec square x, the result is sec x. Now integration of sec x, we have formula for that, that is log of mod of sec x plus tan x, and the limit is from 0 to pi by 3. Now first of all put upper limit, that is pi by 3, and then after lower limit, that is 0. So it will become logarithm of modulus of sec pi by 3 plus tan pi by 3 minus log modulus of sec 0 plus tan 0. Value of sec pi by 3 is 2, tan pi by 3 is root 3, log of mod 2 plus root 3, then after minus sec 0 is 1 and tan 0 is 0, so it will become log 1, and the value of log 1 is 0. So logarithm of modulus of 2 plus root 3. This is the required arc length for the given curve y equals to log sec x from x equals to 0 to pi by 3. Okay. Now consider example number 3, that is the shape of a cable from an antenna tower is given by the equation y equals to 4 by 3 x raised to 3 by 2 from x equals to 0 to x equals to 20. We have to find out the total length of the cable. Now you can see that again this function y equals to 4 by 3 x raised to 3 by t, this is of the form y equals to function of x. So to find out the total length of a cable, we will apply the formula s, that is equals to integration from a to b square root of 1 plus dy by dx the whole square dx. Here the value of a is 0 and b is 20. So square root of 1 as it is plus as it is. Now we have to find out derivative of y with respect to x. So 4 by 3 as it is, and derivative of x raised to 3 by 2, the result is 3 by 2 x raised to 1 by 2. Now you have to simplify this result. Okay. And the simplification of this result is square root of 1 plus 4x. Now we have to integrate 1 plus 4x the whole raised to 1 by 2. To integrate this function, you have to remember the formula integration of x raised to n dx. And integration of x raised to n dx, the result is x raised to n plus 1 over n plus 1. So applying this formula, it will become 1 plus 4x the whole raised to 3 by 2 divided by 3 by 2. And over here the coefficient of x is 4. So you have to divide the result by 4. And the simplification of the denominator is 1 by 6. Then after you have to put down upper limit as 20 and the lower limit is 0. For upper limit 20, the result is 81 raised to 3 by 2, and for the lower limit 0, the result is 1. Now 81 raised to 3 by 2, the result is 729 minus 1, and 729 minus 1, the result is 728, and over it we have 6. So the result is 728 by 6, and after simplification you will get 364 by 3. So this is the required total length of a cable for the function y equals to 4 by 3 x raised to 3 by 2 from x equals to 0 to x equals to 20, right? Now we will discuss second topic, that is component test for conservative field, right? So let f bar equals to f1i plus f2j plus f3k. This is the vector field where f1, f2, f3 have continuous first order partial derivatives. Then the vector field f bar is conservative if the following conditions are satisfied. That is del f1 by del z equals to del f3 by del x, del f2 by del x equals to del f1 by del y, and del f3 by del y, that is equals to del f2 by del z. This test is called component test for conservative field. For the vector field to be conservative, its curl is 0. Curl f bar equals to 0. If we will find out the curl f bar, that will be in determinant ijk del by del x, del by del y, del by del z, then after f1, f2, f3. And if you will find out that determinant, and if you will equate that determinant to 0, you will get this same result, right? So this is nothing but the component test for the vector field to be conservative, right? Now we will take one example related to this topic, that is example number 1. We have to show that this vector field is conservative but using component test, and then after we have to find out the scalar potential function phi for it. So we have been given f bar equals to f1i, say this is f1i, and this is f2j, and this is f3k. So we have f1 equals to e raised to x cos y plus yz, and then after f2 equals to xz minus e raised to x sin y, and f3 equals to xy plus z. So over here we have f1 equals to e raised to x cos y plus yz. So first of all we have to find out del f1 by del y and del f1 by del z for f1. So del f1 by del y, partial derivative of f1 with respect to y. So x and z will be constant. So e raised to x as it is, and derivative of cos y is minus sin y. Derivative of y is 1 and z is constant. So this is del f1 by del y. Now del f1 by del z, so partial derivative of this result with respect to z. So x and y will be constant. So derivative of e raised to x cos y will become 0, and derivative of yz with respect to z, the result is 1 and y is constant. Now for f2, that is xz minus e raised to x sin y, we have to find out del f2 by del x and del f2 by del z. So del f2 by del x, it means partial derivative of this function with respect to x. So z and y will be constant. So derivative of xz with respect to x, the result is z, and derivative of e raised to x is e raised to x, sin y is constant. Now partial derivative of f2 with respect to z, so x and y will be constant. So x as it is, derivative of z is 1, and this is the function of xy, so its derivative will be 0. So del f2 by del z is x. Now for f3 equals to xy plus z, we have to find out del f3 by del x and del f3 by del y. Now del f3 by del x, it means partial derivative of this function with respect to x. The partial derivative of this function with respect to x, so y and z will be constant. So derivative of xy with respect to x, the result is 1 and y is constant, and derivative of z is 0. So the overall result is y. And del f3 by del y, so partial derivative of this function with respect to y, so x and z constant. So x as it is, and derivative of y is 1 and derivative of z is 0. So del f3 by del y, that is x. Now you can see that del f1 by del y and del f2 by del x both are same. See, del f2 by del x, that is z minus e raised to x sin y, and del f1 by del y, that is again z minus e raised to x sin y. So first condition is satisfied. Now you can check for second and third condition also. Del f1 by del z, del f1 by del z and del f3 by del x. See, del f3 by del x, that is y, and del f1 by del z, del f1 by del z, that is again y. So the second condition is also satisfied. Now third condition, del f2 by del z, del f2 by del z is x, del f3 by del y, del f3 by del y is y. So the third condition is also satisfied. It means all conditions are satisfied. So by component test, you can say that the given vector field is conservative. Now if the vector field is conservative, then we have f bar equals to nebula phi. So from this relationship, we will be in a position to find out the scalar potential function phi. So f bar is this vector field, right? And nebula phi, that is gradient phi, that is defined as del phi by del x I cap plus del phi by del y j cap plus del phi by del z k cap. Now by comparison, we have del phi by del x is e raised to x cos y plus yz, del phi by del y is xz minus e raised to x sin y, and del phi by del z is xy plus z, right? Okay, that is written over here. Now integrating equation number 1 with respect to x, so in the left hand side we will be having phi, and integration of e raised to x, result is e raised to x, cos y is constant and yz is constant, and integration of 1 is x, so the result is xyz, and function of yz constant. Now integrating second equation with respect to y, so integration of xz is xyz, and integration of e raised to x sin y, e raised to x is constant, and integration of sin y is minus cos y, so minus minus plus cos y, so it will become e raised to x cos y, and function of xz constant. And finally integrating equation number 3 with respect to z, so integration of xy, the result is xyz, and integration of z, the result is z square by 2, and function of xy constant. So collectively from these three equations we have to write down 5. We have to write down the repeated term only once, that is e raised to x cos y is repeated 2 times, so we will write down it as only once, that is e raised to x cos y, and xyz is repeated 3 times, so we will write down it again 1 time only, that is xyz, and the last term is z square by 2, and these are constant functions, that is function of yz, function of xz, and function of xy, and that is replaced by c. So this is the required scalar potential function. Okay, right? Now the last topic is exact differential form. A differential form f1 dx plus f2 dy plus f3 dz is exact on a domain D if f1 dx plus f2 dy plus f3 dz is d phi for some scalar function phi throughout domain D. and d phi, that is nothing but del phi by del x dx plus del phi by del y dy plus del phi by del z dz, right? So I will make you understand this topic with the help of one example. That is, we have to show that the differential form under the integral, that is this one, is exit in a space and evaluate the integral. For the given integral to be exit, we have to prove f1 dx plus f2 dy plus f3 dz, that is equals to d phi, right? So this is the condition for the differential form f1 dx plus f2 dy plus f3 dz to be exit, right? So first of all, we require f1 dx plus f2 dy plus f3 dz. It means we require f1, f2 and f3. See, this is f bar dot dr bar. This is f bar dot dr bar, and f bar is f1i plus f2j plus f3k, and dr bar is dxi plus dyj plus dzk cap. Now if you will find out the dot product, you will find this result, right? So from here you can say that f1 is e raised to x minus y plus z square. So this is f1, e raised to x minus y plus z square I cap. Then after, f2 is e raised to x minus y plus z square. So minus e raised to x minus y plus z square. This is f2. Then after, plus 2z e raised to x minus y plus z square k cap. So this is f3. So this is f1i plus f2j plus f3k. If you will find out the dot product of this f1i plus f2j plus f3k with dxi plus dyj plus dzk cap, you will get this result. So this is f bar dot dr bar, right? So simply from this you can conclude that this first component is f1, then after second component is f2, and the third component is f3. Now to prove that f1 dx plus f2 dy plus f3 dz is exit in a space, we have to suppose f bar equals to nebula phi. So this is f bar, and nebula phi is del phi by del x I cap plus del phi by del y j cap plus del phi by del z k cap. So from this relationship, first of all, we will find out the scalar potential function phi, and from that we will show that f1 dx plus f2 dy plus f3 dz, that is equals to d phi, right? So that's why we have taken f bar equals to nebula phi. Okay, so by comparison we have del phi by del x is e raised to x minus y plus z square, and del phi by del y is minus e raised to x minus y plus z square, and del phi by del z is 2z e raised to x minus y plus z square. That is written over here, right? This is del phi by del z, that is equals to 2z e raised to x minus y plus z square. Now we will integrate this with respect to x. So in the left hand side we will be having phi, and integration of e raised to x minus y plus z square, the result is e raised to x minus y plus z square divided by 1, and function of y is at constant. Similarly, integrating this one with respect to y, so the result is phi equals to minus e raised to x minus y plus z square, and the coefficient of y is minus 1, so dividing it by minus 1, and function of x at constant, so minus minus will cancel out. So this is the required result for function phi. Then after, finally we have to integrate this function partially with respect to z, right? Then after, in the left hand side we will be having phi. Now to integrate this function, we have to remember this formula, that is integration of e raised to function of x into f dash x dx, that is equals to e raised to fx plus c, right? Here e raised to fx, this is fx, and derivative of fx. It means derivative of x minus y plus z square, the result is 2z. So e raised to x minus y plus z square is f of x, and derivative of this f of x is 2z in this way. So overall integration of this function will become e raised to f of x, and f of x is x minus y plus z square, and function of xy is constant, right? Okay, so overall function phi, that will be, here e raised to x minus y plus z square is repeated 3 times. So we will write down it only once. So the required function phi, that is e raised to x minus y plus z square plus c. Now we will find out d phi, and d phi, that is del phi by del x dx plus del phi by del y dy plus del phi by del z dz. Okay. So we have to find out del phi by del x, and del phi by del x means partial derivative of this function with respect to x. So derivative of e raised to x minus y plus z square, that will be e raised to x minus y plus z square, and derivative of x is 1, dx as it is. Now del phi by del y, it means partial derivative of this function with respect to y. So e raised to x minus y plus z square as it is, and derivative of minus y is minus 1, and derivative of x at z square, that will become 0, and dy as it is, plus del phi by del z. So partial derivative of this function with respect to z. So e raised to x minus y plus z square as it is, and derivative of z square is 2z dz, right? Now you can see that this is nothing but f1. This is nothing but f1, and minus of e raised to x minus y plus z square, that is nothing but f2, and this is nothing but f3. So we have got the result d phi equals to f1 dx plus f2 dy plus f3 dz. So from this condition we can say that the given integral is xz. Now we have to find out the value of the integration. The integration is from a to b f bar dot dr bar, and f bar dot dr bar, that is nothing but d phi, as the given integration is xz, right? So f bar dr bar, that is nothing but f1 dx plus f2 dy plus f3 dz, and that is equals to d phi, as the given integration is xz, right? And a and b are the points given to us, that is 0, minus 1, 1 to 2, 4, 0. Now integration of 1 with respect to phi, answer is phi, and this is upper limit, this is lower limit. Now replace phi by e raised to x minus y plus z square plus c, and this is upper limit and this is lower limit. Replace x by 2, y by 4 and z by 0 for upper limit, and for lower limit replace x by 0, y by minus 1 and z by 1, and simplify the result. You will get e raised to minus 2 minus e square. So this is the result of this integration, or the given integration, right? Thank you for watching this video.